Can the chat hear me? Okay, folks, let's get started. So this afternoon, 5 o'clock, the first midterm exam is going to be released to you. It is fully written. I am going to do a run-through, a dry run this afternoon, just to make sure there aren't any mistakes in it that I need to deal with, and to get a good sense of how long it's going to take somebody who knows what they're doing to be able to complete the exam, to make sure that the length is okay. So I might end up modifying slightly as a result of that. On Blackboard, all the info's up there about it. There's a new section in Blackboard called Exams. Once you start the exam, you'll have 3 hours to complete it. And before you start the exam, make sure you have downloaded and familiarized yourself with the system information document. This is explained in Blackboard. Any clarifying questions you need on the systems, even before you open the exam, feel free to use Piazza or my office hours to ask any clarifying questions about them. Okay, tomorrow homework 5 is due, and then the exam itself is due Sunday at 5. Any logistical stuff before we get into the content? I don't have a huge amount of muddiest points to go over today, so there should be plenty of time to go over any questions you have on that system information document or anything else related to the exam. Yeah.
Where do you find the system information?
So let me show you here where to find it. So So if we go into Blackboard, okay. So there are a couple different ways you can get to it. One of them is the Resources tab over here, which will take you to several resources, including the system information document right here. The other place is to go to the Exams tab here. You see there is a folder in here for Midterm Exam 1, which is where the exam itself is going to end up appearing. And I have some stuff to look at before the exam, you start the exam here, as well as a link to the system information document here as well. So a couple different ways you can get to it. Okay. Any other logistical stuff to talk about before we get into the content? Okay, so all of the muddiest points this time were on kinetic stuff, I assume because of the homework assignment that's underway. So let's tackle those. So in the reaction rates content video, one of the questions I asked had mentioned what's the speed or velocity of something. And the concern was from physics that I thought those were different things. Well, so to clarify that, velocity is the change in position with respect to time, but position is a three-dimensional vector. And so the result of this, the velocity is going to have two components to it, a magnitude and a direction. The speed is simply the magnitude of the velocity. So so they contain the same information, it's just that the velocity has the extra information of the direction that it's going. Anybody have clarifying questions on that issue? I mean, we're not using an actual speed or an actual velocity in chemistry. What we're using is the idea of a change in something with respect to time for the rates of reaction. Okay. All right. When working on reaction rates and discussing the consumption rate based off an equation, why do we put the coefficients into a fraction? So for example, 8 aluminums become 1/8 concentration of aluminum when writing the equation. Okay, so this is getting at the question of, if we have, let's say we have coefficient A times species A, coefficient B times species C goes to form, let's be consistent, C plus D. And we are trying to express the rates of each of these components with respect to time compared to the rate. So the idea here, let's start with C. We want to have something having to do with the concentration of C changing with respect to time. Now, C is a product, so it is increasing in concentration as the reaction proceeds. And as the reaction proceeds, we would like for the rate to be a positive number. So we don't need to put a negative sign in front of this because an increasing C would be a positive rate, which is what we want. But we also want to be able to talk about the reaction happening in terms of like 1 unit of the reaction happening. And so each time the reaction happens, you get C molecules of C formed. So if the rate here is how rapidly the reaction is happening, we have to divide this rate by C, the lowercase c. So that if let's say if C is 2, then, and you are making 2 C's every second, then the reaction is happening 1 time every second. Does that make some sense? So that's why we are dividing by the C. And so this is the same as 1 over d, dd, dt, and negative 1 over a, dA, dt, and negative 1 over b, dB, dt. And these have to be equal to each other because if we look at, for example, at each time the reaction happens, we make 2 C's, we also make 3 D's. Well, then 1/3 of the formation rate of D would be the 1 per second. 1/2 of the formation rate of C would be 1 per second. So that gives us the 1 per second for the R, the rate that's happening. Does that general idea make some sense? So why we are doing 1 over? Okay. Any no other clarifying questions on that part? Okay. All right. There was a question posted from the homework this week, part B, an example question that's on the method of initial rates. And so this is the example question. Nope, that's brightness. Let me zoom in a little bit so you can see it a little better. Okay. I'll try to not move this too far. Okay, so the idea here is to use some tabulated information with initial concentrations of these of the 2 reactants. So these really should be labeled as initial concentrations. And we are given the initial rate of this. So this is the change in concentration with respect to time, which I would write as dA dt instead of the deltas. And this also ought to be identified as the initial rate of this happening rather than just any sort of rate. And so the idea here is we want to find out from this data what our rate law is going to be. So the general idea is that we are going to assume that the rate law is of the form K times concentration of A to some power times concentration of B to some power. And so finding the rate law comes down to determining the values of A, B, and K. So let's take a look at the reactions that we have here. In this, comparing 1 to 2, we left concentration of A the same, and we change the concentration of B, but the rate did not change. What does that tell you about the dependence of the rate law on B, on the concentration of B? So if this is the rate law, and you change B like we did here, and the rate doesn't change, what's got to be going on here? Yep, someone from the chat says that B has to be 0. Right. So if the concentration changes, but this doesn't, then we need to raise B to the 0th power so that it just drops out. So our rate is K, concentration of A, to the A power. Make some sense? Okay. So now let's look at the case of comparing reaction 1 to reaction 3. So we're changing the concentration of A. We are leaving the concentration of B the same. But here we do get a difference in the rates. So we need to take our rate laws and compare them some way. So what we do is we're going to write this as R2 over R1. So no, let me label that 3 since we're actually talking about trial 3. So then that is going to be K times the concentration of A for trial 3 to the 8th power over K concentration of A in the first trial to the 8th power. Okay. Notice that the K's cancel. Right. So what we now can plug in our numbers. So we have R3 over R2, and so I'm going to pull out a calculator. We are going to, so this is going to be 3.9625092. I don't think we need that many digits, divided by 2.29311,875. And we don't have to put in the times 10 to the negative 7th because those are it's going to be both in the numerator and the denominator, and they're going to cancel. And we get, for this side, 1.728. And that's going to equal the concentration of A in trial 3 over the concentration of A in trial 1, the whole thing to the 8th power, because we can take, if we have X over Y, each of them to the Z, then that is the same as X over Y to the Z. So let's take concentration of A in trial 3, which is 0.078, divided by the concentration of A in trial 1, 0.065, and we get 1.2 to the A power. Okay. Now, in the other examples I've worked in class and that I did in the video that introduced this method, I specifically chose changing the concentrations by a factor that was a nice integer. So I doubled it, for example. And so if you double this and then this doubles, then just by looking at it, you can say, okay, the exponent has to be a 1. But in this case, we didn't double it. And so it's not as easy to see what's going on. So the trick we play at this point is to take natural logarithms of both sides. So actually, it can be any kind of logarithm as long as you use the same kind on either side. So if we take the log of 1.728 equals the log of 1.2 to the A power. Remember how logs work. If we have, let me bring it down here. If we have the log of x to the y, that equals y times the log of x. So we can bring that A out in front. So let's get rid of that and put the A right there. Now we take the two numbers. Let me get another sheet of paper. Showing up. So if we take, hello, calculator switch. There we go, finally. All right, 1.728, and I will take the log base 10 of that. It doesn't matter which log we use, as long as we do the same thing on both sides. 0.2375 equals A times the log of 1.2. Log base 10 of that gives us 0.07918. So then A has to be divide through. So 0.2375 divided by 0.07918, and we get 2.999, which is extremely close to 3. So we now know that our rate law is going to be, let me zoom this out. We now know that our rate law is going to be K times concentration of A to the third power. The last thing we have to do now is to determine the value of K. So for that, we simply use any of these trials. Because we have a rate, we have a concentration of A, you plug them in, and you get the value of K, because that's the only thing that's not known. So it would be something like 2.29 times 10 to the negative 7, and that's in units of molar per second, equals K times the concentration of A, so I'm doing the first one, times 0.065 molar to the third power. So we raise that to the third power, divide. So we have 0.065 cubed, 2.29 times 10 to the negative 7. And because I divided them the other way around, I take 1 over that, and we find that K equals 8.33 times 10 to the negative 1, 2, 3, 4. And now we need to figure out our units. So this was molar per second. So and there's no seconds over here, so we know that K is going to have a per second involved. We have a molar here. This becomes a molar cubed. So molar divided by molar cubed gives us a molar to the minus 2. Okay. So, and if we had chosen a different trial here to do this calculation on, we would have gotten the same K. So that is the method of initial rates. And so that is the approach that you use to answer this kind of question. Any clarifying questions on this?
Someone asked what would we do if A and B were different and the rate law was 2? So like you didn't have 2 trials where your concentration of A was the same.
Right. So what do you do if in all of the trials more than one of these species is changing at a time? Well, then you set up the experiment wrong. So you would not, you cannot use the method of initial rates if in each trial more than one thing is varying. You have to set it up so that one species is held constant across a pair of trials, or all but one are held constant across a pair of trials. Anything else? Okay, so that is method of initial rates. Will there ever be a time when the exponents aren't 1, 2, 3, and therefore aren't first, second, third order? I would add 0 to that list. Those are by far the most common exponents. It is possible for there to be other exponents. It is possible for an exponent to be negative, for example. -1 is actually pretty common. It's possible for an exponent to be a fraction. A half, 1/2 is not unheard of. But those cases are rarer than 0, 1, 2, and 3, and we don't tend to look at integrated rate laws in those cases. The only integrated rate laws we're discussing are the 0, 1, and 2. We're not even talking about the 3 case. But the method we just went through, this method of initial rates, would still successfully get you to the answer, the correct order, even if it is not 0, 1, 2, or 3. This method works regardless. Because you're solving an equation here for A, it can be anything.
The one we just solved would be considered third order, and how would that apply to graphical?
Okay, yes, that would be, that case we just solved would be considered third order. And because it is not 0, 1, or 2, we have not covered an integrated rate law for it. And so we don't have a graphical approach to analyzing that particular one. Now, you could certainly develop such a graphical approach by solving the differential rate law, but third order reactions are uncommon enough that, it wasn't worth going through that as yet another example of it. And I'm not going to throw an integrated form of the third order at you. Okay. All right. How do we know when to use the integrated rate laws and to make the graphs? Will they be provided on a specific question or have an equation saying to use it? So it is a question of what information are you given. If you are given a table like this, then it's pretty clearly expecting you to use the method of initial rates instead of integrated rate laws. If, on the other hand, you are given data, a table of data, where you have concentration at different times, so 1, 2, 3, 4, and then you've got some values here, then at that point it would make sense to try plotting the concentration versus time, plotting the natural log of the concentration versus time, and plotting 1 over the concentration versus time to see if any of those are straight lines. So it's a question of what type of information you're given. So the difference here is you are given the concentration, versus here you're given a rate. So when you're given a rate, you use the differential forms of the rate laws. When you're given the concentrations, you use the integrated forms of the rate laws. Does that really make some sense? Okay. All right. Half-lives. Understanding the general idea, but not getting the first/second order parts of it. Okay, so the issue with half-lives is that if you look at the first order case, okay, the half-life means the time, so we'll call this the half-life, when the concentration becomes half of the original concentration, so we will call this half of that. Okay. If we take this equation and then try to simplify it, we notice that the a naughts cancel. And so 1/2 equals e to the minus kt 1/2. We can take the natural log of both sides. So natural log of 1/2 equals negative kt 1/2. And then you just do some manipulations here to get t 1/2, the half-life, equals negative log of 1/2 over k. And then you can do further manipulations if you want by taking the negative inside the log, so this becomes the natural log of 2, because it raises the 1/2 to a negative 1 power. And so then you now have an expression for the half-life. Now, the key thing is when we do this, the a naught completely left the equation. So what that means is that for a given first-order reaction, the half-life is an alternate way of providing the same information as the rate constant. And as a result, and because the half-life is a more kind of intuitive idea, it tells you it's a more convenient way to describe the rate of the reaction. If you say something has a half-life of a day, then you know right off the bat that however much you start with, after a day, half of it is gone. If the half-life is a microsecond, then that tells you very quickly that after a second, there's going to be nothing left, right? So the half-life is a very useful concept in this case. So that's first order. Second order, we have 1 over concentration of A equals 1 over concentration of A naught plus KT. Well, we do the same thing we did before. Call this the half-life, and we're going to make this now half of the initial concentration, which we can do by doing that. Okay. So we now have KT 1/2 equals 2 over A naught minus 1 over A naught is 1 over A naught. And so T 1/2 equals 1 over K times concentration of A naught. And so when we did exactly the same thing to this equation, the key point is that the A naught did not go away in this case. So for a second order reaction, you can't say that the second order reaction has a specific half-life, because you have to know how much you started with. The half-life changes depending on how much of the compound you have at a particular time. So in the first order case, half-lives are useful because they let you present the information in a way that makes sense. In the second order case and in the 0th order case, half-lives are not useful because they actually don't tell you the same information as K unless you already know how much you're starting with. Okay. Any clarifications on half-lives? Okay. All right, so that's all the muddiest points that I had. So let's open up the floor to absolutely anything in the chat. Flooding, method of flooding, okay? So general idea of the method of flooding is that it's an alternate way compared to the method of initial rates for determining the rate law of a reaction. So let's suppose we have A plus B plus C goes to products of some kind. And we are monitoring the concentration of A. So we measure dA dt, so negative dA dt, and we expect this to have a rate law of K concentration of A to some power, concentration of B to some power, concentration of C to some power. The idea of the method of flooding is that for all but one of the species, we make the concentrations really large. So if we take initial concentration of B to be something like, let's say, 0.5 molar, concentration of C to be 0.5 molar, and then we'll make the initial concentration of A something very small. So 0.001 molar, something like that. Okay. Once the reaction has run to completion, the A is the limiting reagent, so all of that will be gone. So our concentration of A final is going to be 0. But from stoichiometry up here, we know that for every molecule of A that reacts, one molecule of B is going to react. And of course, obviously you would modify this if it was a stoichiometry different from what you have there. So we know that the concentration of B final is going to be 0.5 minus 0.001, because that's how much B will react away. So that's 0.499 molar. Concentration of C final is going to be 0.499 molar. So what we have done is we have flooded the system with B and C. And as a result of that, their concentrations are effectively constant over the entire course of the reaction. What we can therefore do is look at this expression here and say, this is a constant, this is a constant, this is a constant under these conditions. And so let's fold them all together so that we have something we're going to call K observed, off the side. K observed is going to be K concentration of B to the B, concentration of C to the C, and then that lets us rewrite our rate. So our rate is going to now be K observed times the concentration of A to the A. What this does is that for this set of conditions, we've taken a complicated rate law and broken it down so that only one concentration matters. And now we can look at this one by itself and say, what kind of reaction is it? So under these conditions, we measure this concentration as a function of time, and we plot it. So we can do our concentration of A versus time. We can do our natural log concentration of A versus time, and we can do our 1 over concentration of A versus time, and we see which one of these is a straight line. And let's suppose that this is the one we see. That means that we now know that this equals 1, because the natural log versus time is the first order version. Okay. We also know from this plot that the slope is negative K. In this case, that K is K observed. So what you do next, okay, so what that means here is that the reaction is first order in A, reaction is first order in A, and this is therefore known as a pseudo first order rate coefficient. Because it's not really a rate coefficient because it has these concentrations that are part of it, But in terms of the functional form of this equation, it's acting like one under these flooding conditions. So what we can do, though, is we can flood with different amounts of B and C. If B were 0.3 instead of 0.5, it would still be flooded, because if this were 0.3, then this would be 0.299, and so it's still flooded. But our value of K observed is going to be different because we've changed the concentration of B that's in here. So what you do then is you do this experiment multiple times for different concentrations of B that are all flooding. And you get the K observed in each case. And so you can then plot your K observed as a function of concentration of B that you started with, where all of them are flooding, and you're going to get different values. Now, the way I've drawn it here, it looks like a straight line going through 0. So if we look at our form of K observed, equals K concentration of B to some power times concentration of C to some power, but C is not changing in this set. We're just changing how much B there is. We're leaving C at the same value. So those are constants. And if we get a straight line, then that means that B has to be 1 because it's a linear equation, and the slope is K times this, but we don't even need that piece of information. So now, having done this experiment, we now know A equals 1 and B equals 1. Well, you can leave B constant and then change the values of C to do exactly the same thing. So you do K observed, concentration of C, and this time let's suppose that we get something that looks like this. That's clearly not linear in this case. And let's suppose that this, in this case, is quadratic. If the experiment shows you that it's quadratic, then you now know that C is going to be 2. At that point, you now have your rate law. The rate equals K, concentration of A to the 1, concentration of B to the 1, concentration of C to the 2. And then for any of these data points, any of them, you can plug in the initial concentrations of everything. You can plug in the rate, and you can get K. Or actually, probably easier is you go to your K observed, because you have the K observed values already determined. You plug in K observed, you know this is a 1, you know this is a 2. You plug in the concentrations you have, and so you get K. So that is the method of flooding. It is a very powerful tool because it takes a complicated rate law and isolates one species at a time that is changing. Okay. Horizontal K observed versus time would indicate 0 order. Yes, that is correct. So if the K observed versus concentration of some species did not change with the concentration of that species, then yes, that would be 0th order in that particular species. Now, how do you look at this and say, oh, okay, it's curving, it must be quadratic? Well, the easiest thing to do is to say, what is a quadratic? Second order is most likely, but quadratic would be saying that we have concentration of C squared that's affecting K observed. So what you could do then is do the square root of K observed, versus concentration of C. And that would take that, if it is quadratic, and turn it into a straight line. And if it's a straight line, then you know it's quadratic. If that doesn't work and it's still going up, then maybe it's third order, so then you would do the third root to see if you got a straight line. Okay. Anything else on flooding? All right, what else can we talk about? Would you guys like me to pull up the system information document and we can look through parts of it together? See a couple nods. All right, give me that. All right. Okay, so we have 4 systems that are going to be covered on, not covered, that are going to form the context for the questions that are being asked for the exam. The first one is seawater, and the information that I am providing you with here are the concentrations of the main ions that are in seawater. Now, the units here are parts per thousand by mass, which is not the typical unit of measurement that chemists tend to use. So, so being able to convert from parts per thousand by mass to something that is more chemistry oriented, like molarity or molality, would probably be a good thing to think about. Hopefully you are familiar with what all of these ions are, with the possible exception here of borate, so I'm identifying that for you for which one it is. And then I'm also giving you a table here that looks at all of the various combinations of cation and anion you could have, and what the solubility of the ionic compound that is formed for each one of those. And so these solubilities are in units of grams per 100 milliliters of water. And so that is the background information that I'm providing on System 1, seawater. Now, with that being the set of information that I'm providing, what kinds of questions can you think of that I could be asking you about it? One of them, I hope is, I've already mentioned, is you probably need to get these concentrations out of whatever units these are and into something that is more convenient for a chemist to use. But that's probably going to be a step along the way towards other kinds of questions that are going on. What other kinds of things could be asked about this kind of information? Out of all the material we've covered. So, chat says, cation size based on packing order size of unit cell. Oh, that's a question? Okay. So yeah, we can go back and look at those, although that's going to end up relating to one of the other systems that we're looking at in just a minute. Yeah, where have we used solutes before in class, in any of the maybe Newton homeworks? What was the main topic last week? Chat says concentration and dilution, colligative properties. Yep, concentration, dilution, definitely. Colligative properties, definitely. What determines whether something dissolves or not? So if I did something like saying, boy, magnesium chloride sure has a big number here. Strontium bromide sure has a small number here. What does that difference suggest about the compounds or ions that are involved? Where would you go with that with that kind of question? So a suggestion from the chat is polarity. So let's generalize that a bit, intermolecular forces. Okay. So you'd see what could you determine about intermolecular forces that might be different in the magnesium chloride case versus the strontium bromide, actually I meant strontium bicarbonate, but what could be different between those? So probably a better question might be something like looking at maybe let's look at calcium fluoride versus calcium chloride, because there you're keeping the calcium the same, but the fluoride is different, and the chloride are different, though they're in the same column, the same group. But yet it's a huge difference in solubility. And so since chlorine and fluorine are in the same group, what's the biggest difference between them? So from the chat, there's a suggestion of electronegativity. That is certainly a difference between them. But electronegativity is the tendency for an atom to hold onto electrons within a covalent bond. And this does not have a covalent bond involved. So when you take any element and go down a period, what's changing? Certainly the masses, absolutely. The masses don't have a huge impact on intermolecular forces, though. What aspect is changing that goes down that does have an impact on the intermolecular forces? Number of electrons, right. Each time you go down to the next period, you are adding an entirely new shell of electrons that are part of the core. The more electrons you have, the stronger, the more polarizable that electron cloud is, meaning the stronger induced dipoles you can have. So, and remember, induced dipoles include London dispersion forces because that's induced dipole, induced dipole. So those are some kinds of questions that could be asked from System 1. System 2 on here is looking at ionic crystal structures. And what we're specifically looking at is a combination of the main ions from the alkaline earth group, so group 2, and the chalcogenides, which is the oxygen group, or group 6. And we're looking at comparisons between the two. And so the idea is that the anions here tend to be larger than the cations. So the anions form, in this case, we're saying a face-centered cubic structure, and that the cations fit into the octahedral holes, the octahedral interstices, and I tell you where those octahedral interstices are, and I point you to a place you can go to have a 3D image you can grab with your mouse and move around so you can visualize what's going on. And then I give you extra information here at the bottom saying that because all anions are charged the same, and because like charges repel one another, the cation size typically needs to be larger than the size of the hole in order to force the anions to be separated by at least some space. So what that means is that if you do something to figure out the size of those holes, those interstices, then that's going to be the minimum size for the cation that would go in there. Hopefully, looking at this information that I'm providing here, you can guess at least several of the types of questions I'm going to be asking you. How big's the hole? Which of these work? Which combinations work and which ones don't? That would certainly be a place to start, right? The third system we're looking at is the surface level atmospheres of Mars and Venus. And so we've got the composition of each of the atmospheres by the various gases. And it's kind of interesting how very similar their atmospheres are, despite the fact that there is a maybe almost 4 order of magnitude difference in the pressures at the surfaces. But the ratio of the compositions are nearly identical. I also give you the temperatures. So if I'm giving you temperatures and pressures here, what subject matter that we covered in the first 4 weeks seems to be the most relevant to this? Chat says phase diagrams. Absolutely, phase diagrams. Understanding phase transitions, which phases are going to be present in various places. So I'm probably going to give you some phase diagrams on the exam that relate to this, and then ask you some things about what's going to happen on Mars, what's going to happen on Venus about these. And what other main topic did we cover when we went through phase diagrams? What other kind of graph did we do? Cooling curves, or the flip side of that, heating curves. Absolutely. So again, in this kind of problem, you can probably predict, I would guess, about half of the questions I'm going to be asking you. Okay. The final system we're looking at is hydrofluorocarbons. And so these are compounds that have this structure, CXHYFZ. And in particular, I'm looking at all of the cases where C is 1 or 2. These are based on methane and ethane, and I point you to places you can get 3D models of them to grab with the mouse and manipulate. And I also point you to a place you can go to get the 3D models of the specific compounds here so that you can see things like this, where you can see which side the various fluorines are on. Okay. So, and then notice I'm as well giving you the boiling points of all of these compounds. Okay. So, what kinds of questions do you think I might ask related to this topic, this system? Chat says intermolecular forces. Absolutely. This system is pretty clearly directly set up to talk about intermolecular forces. And so, consequently, things like explaining the boiling points, but then what else what else do intermolecular forces apply to? Not just boiling point, but also what? Chat says colligative properties. I'm going to say no on colligative properties because that would, if colligative properties did depend on the nature of the intermolecular forces, then that would imply that the type of solute mattered, but the whole point of a colligative property is that only the number of solute particles matter. So, so probably not colligative properties with respect to this system. But we have at least 4 or 5 other things other than just boiling point that intermolecular forces relate to. What other phase transitions are there? Very quiet group. Well, we have melting. We have vapor pressure. We have solubility. If you're looking at, if you're comparing intermolecular forces between 2 different molecules, and you certainly have plenty of different molecules here. We might have viscosity. We could have adhesion to surfaces, which result in things like capillary action, capillary rise. All of those are things that intermolecular forces relate to. So this question seems sort of tailor-made for that kind of, those kinds of questions. So, so even before you start the exam, you should be able to look at this list of systems and be able to predict the kinds of questions that are likely to be asked about these. And you have opportunities then to ask me clarifying questions or ask clarifying questions on Piazza, which I'm going to be monitoring, you know, pretty close to constantly tomorrow and over the weekend, so that any questions that come up I can handle. And so that you would be able to go into taking the exam prepared for the kinds of questions you're likely to see, because you can do some pretty good predicting of what's going to be there. Okay, we have about 10 minutes left. What else can we talk about? Yes?
Just a quick question on the exam. Do you say, are we going to get it graded directly after we turn it in, or is this coming after?
I haven't set that up yet. I think that I am going to set it up so that the grades become available to you when it closes at 5 on Sunday. That's just a minor, you know, sort of anti-cheating thing, so that, you know, if I know I did really well versus, oh, I really screwed a lot of it up, that somebody talking to somebody else could give that information about what worked and what didn't. And so I'm not, you know, I'm assuming that everyone is going to be honest in how they're dealing with things, and I'm believing that enough that I'm not doing anything like lockdown browsers or proctoring services or anything like that. But a little thing like you can see the grades at 5 on Sunday, I think is a reasonable thing to do.
Like you keep posing the, like, I guess how big of an atom can fit in the spaces between.
Okay.
Can you just give like a general overview?
Sure, absolutely. So I did go through an example like this yesterday using the body-centered cubic example. So because the exam question is the face-centered cubic, I don't want to do that example specifically here in class, because the goal is for you to be able to go through that thought process. But I'm happy to go through a different example that looks at it. So the idea would be, if we have our face-centered cubic lattice, so I'm going to draw this in 2 different ways. I'm sorry, but yeah, body-centered cubic. So we have an atom at each corner, an anion at each corner. And we have an anion dead center that if we draw the connecting lines, is kind of dead center here. The second way to draw it is when you're using the space filling kind of picture, which is certainly harder to draw. So in the space filling picture for body-centered cubic, let me label it. The corner atoms are not touching each other because there is a central atom in the middle here that has expanded the lattice. And if we look at the points where it's contacting, we can tell that it's contacting with the central atom is contacting with each corner. So we have a body diagonal that goes through here to that side. And if we just look at that body diagonal, so if we draw the body diagonal here, then we have the central atom, which has one radius here, one radius here. And then we have the corner atom, which has one radius here, and a corner atom here, which has one radius there. Our body diagonal is 4R. And we'll label this RA as the radius of the anion. Now, we can as well do try to find the face diagonal and then find the edge length, which we are going to need in a minute. So if we draw across the bottom this face diagonal, it's going back that way, then we can see that we have a right triangle right here. So that right triangle looks like this. So this is an edge. This is the diagonal of the body, and this is the diagonal of the face that's on the bottom. Okay, it's a right triangle. So from Pythagorean theorem, we know that the diagonal of the body squared is equal to the edge squared plus the face diagonal squared. Okay. We also know that a face diagonal, so up here, gives us a right triangle along the face. So we have an edge, and the face diagonal. So we have df squared equals e squared plus e squared. So let's simplify. This equals 2e squared. Okay, well, now, let's not even bother with the square root at this point. Let's plug this into here. We now have 2e squared plus e squared equals the body diagonal squared, right? So 3e squared equals the body diagonal squared. We know that the body diagonal, we got that over here, is 4RA. So this is 16RA squared equals 3e squared. Now, so we can find E in terms of RA or RA in terms of E. We can go either way we need to go with that just by taking the square root and moving either the 3 or the 16 to the other side. The next thing we need to know is where are the holes that we're going to be dealing with? Well, in this case, hopefully you can see that the biggest holes are in the centers of the faces. And this is the kind of information I would tell you rather than having you try to figure that out. I would tell you that where they are. So if that's the case, and if we have a cation that is going to be in that center of the face, then we can see that this face diagonal that we have, the face diagonal, is going to be this straight line here. We are going to have a radius of the anion here. We're going to have a radius of the anion here. And then we're going to have 2 times the radius of the cation here along the face diagonal. Does that make some sense? So if we're trying to figure out RC, let's see what our face diagonal is. We have our face diagonal here is, face diagonal is going to be square root of 2 times the edge length from this. And we know that that is now going to be 2RA plus 2RC, right? Now, we also have our edge expression here in terms of RA. So let's solve that for this. So I don't know why I have 2 equal signs. So if we solve this for E, we can see that E squared equals 16/3 RA squared. And so E equals 4 over the square root of 3 RA. That can get plugged in here. We now have square root of 2 times 4 over square root of 3 times RA equals 2RA plus 2RC. So now this is just some algebra and plugging some square roots and things into a calculator. You can find an expression for RC as some decimal value times RA, right? So that tells you that whatever your anion radius is, the hole size is going to be some fraction of it by whatever this value is that you get through here. And so that will tell you which ions will work in that hole and which ones won't. Okay. General idea makes some sense? Okay, so it is some geometry to do it and recognizing and some algebra to move the equations around. But it's not as though it's moving, it's not as though you have to use any trig for it. The most complicated part of the algebra that you're doing, or the geometry that you're doing, is the Pythagorean theorem. The only thing you really need to do other than some algebra. And like I said, if it's hard for you to visualize which things are touching and which things aren't, that's a reason why I gave you links to 3D versions of these structures that you can grab with the mouse and move around so that you can really try to wrap your head around the, what the structures are and see what's touching.
And those would be slightly split out of these, and that would need to be equal or slightly bigger, or equal or slightly bigger?
They would need to be larger because, so the idea is that with something that is smaller or equal to that size, then the anions would be in direct contact with each other. And that's not going to happen because they are the same charge and so they repel each other. You need to have something in that interstices that is slightly too big for, or at least somewhat too big for that hole in order to push the anions away from each other. Okay. All right, we are out of time. Thank you all. We do have office hours tomorrow. I believe it's from 10 to 11 if anybody has questions before they get started on the exam. And like I said, I'll be monitoring Piazza pretty constantly tomorrow and over the weekend.